Hi class. Last lectures, we learned about the relative motion analysis of the velocity, and we used the instantaneous center of zero velocity as a method. And previously also we used the relative motion analysis velocity as well as the geometrical method. Today, in this lecture, we'll learn about the relative motion analysis and how to find the acceleration. So this is a continuation of the relative motion analysis velocity, a similar concept, and we'll take some examples. So the activity will be divided in two folds. The first one is to find the translation and rotation component of acceleration, relative acceleration analysis in some examples, and also second fold is the roll without slip motion. So you will have two videos back to back. The second example, let's examine this window mechanism, which is comprised of two linkages, linkage AB and linkage AC. The hinge at C is fixed and free to rotate, meaning that link AC is undergoing pure rotation. However, link BA is undergoing general motion because B is sliding and A is rotating. The question becomes, knowing that link AC is rotating about C, then we know from previous lectures that point A is having a circular path as the link AC is moving under angular velocity and angular acceleration. Therefore, we can divide the acceleration at that point into two components. One is tangential, tangent to the path, and the other one is normal, which is pointing toward the concave part of the circle or pointing to the center of that circle. And also, since link BA is undergoing general motion and it's jointly sharing point A with link AC, we can examine the link AB knowing that B is sliding, meaning we know its direction, and we know also that A has two components which are obtained from the analysis of AC. So it's a similar fashion. I don't expect this lecture to be long since we are building on the same previous method. So let's get into section 16.7, which is the last section of chapter 16, and that will conclude the kinematic analysis of rigid body. In the past, we looked at the relative motion analysis velocity, where we related the velocity of a point A on a link or in a rigid body and B, right? So we have 2 points, we are having a relationship between them through the relative motion analysis, where the velocity of a point, say point B, is equal to absolute relative velocity or absolute velocity of point A plus the relative velocity between B and A. So know that when we write VB, it means absolute velocity, and VA is absolute velocity, and VB relative to A is the velocity of B as seen by A. So your base is A. When you take the derivative, you're still considering the absolute coordinate system, where derivative of VB with relative to time is going to give you the absolute acceleration of that point, as well as the derivative of point A is going to give you the absolute velocity of point A, B and A. However, the relative velocity, the derivative of relative velocity with respect to time has two components. As seen before, we can divide that into two components orthogonal to each other. And the most common one, easy to comprehend, we will be using tangential and normal. So we have two components, tangential and normal. Knowing that this is absolute coordinate, this is absolute, this is relative. All right. Now let's take a schematic or graphic and explain this in more detail. Consider this link AB, and I want to find the velocity of or the acceleration of point B. Well, point B is following a path, and this instant it's located at this location B, as well as point A. Now, since this is in general, we can assume that it's undergoing general motion, meaning translation and rotation. Therefore, we can fix or assume that we know the velocity, angular velocity and angular acceleration, omega and alpha. Now we want to find the acceleration of B, and that can be calculated as equal to acceleration of A plus acceleration of B relative to A, which has two components, tangential component, which is tangent to the path, right? And also normal component, which is pointing from B to A, because A is, think of it as the center of rotation, right? Because we're measuring B relative to A. So B relative to A simply has two components, tangential, B relative to A tangent, and a normal one. So the resultant is B relative to A vector, depending on these values. Now, we learned that tangential component of, in general, of object undergoing rotation is simply can be calculated by the angular acceleration cross product with the vector RB relative to A. RB relative to A. So think of it, this is the base, so the vector is going from A to B. So this is a cross product that will lead us to know the tangential component. And also, alpha is a vector. So these are two vector multiplication, two vector cross product. All right, now the relative normal acceleration component. Now the second component of the acceleration or relative acceleration B with respect to A is the normal. Now again, this normal component, as we learned from the analysis of a point rotating about a fixed axis, has a normal component that is pointed toward the center, and that is equal V squared over rho, or V, you know, it's pure rotation, relative rotation, so it's omega by or cross R, or omega by R over rho. So when you square it, so it's going to be omega squared R squared over R. So you're going to end up with omega squared over R, or divided, multiplied by R. Now, since R is pointing from A to B, and we know that this component is in the opposite direction, so we put a negative. And we keep the relative position of B with A. So that's going to give you the second component, and it's always directed from B to A. So it's important to understand the concept more than knowing the symbols, because symbols can change, the names can change, just know what it means. So in summary, what we have is the acceleration of a point B is equal to absolute acceleration of point A plus the tangent component alpha cross RB relative to A minus omega square RB relative to A. So we need to make sure this is cross product, and that is simple multiplication. All right. Application. In applying the relative acceleration equation, typically there should be some known and unknowns. Let's consider this problem. Say that this mechanism is being fed by an external actuator that provides a known acceleration, angular acceleration alpha, and angular velocity omega. Now, because this is being fed by this lever AB, or into the AB, we want to find, let's say, the acceleration of C, the piston, how much accelerate at any time. Now, the analysis will take into different steps, and we will take an example of that. Now, because AB is a simple rotation and BC is a simple, or it's a general motion, and C is the translation, there is a correlation between this length BC and AB, which is the joint B, so because it's same. So what we will do in the analysis is first find the velocity and the acceleration of point B as seen by AB, meaning let's say we'll start with the acceleration of point B. Acceleration of point B, because it's a tangent to that path, is equal to acceleration of point A, which is 0, plus the relative acceleration of point B relative to A, which has two components. The first one is tangential, equal to alpha cross R B relative to A, so this is the vector going from A to B, minus omega square, which let's say it's known, multiplied by the A B vector R or RAB. So that's going to give you the acceleration of point A, B. Now the next step is I want to relate this point to C. So velocity, the acceleration of AC is going to be equal to, and I'm just breaking it down, so I want you to connect to these thoughts, equal to AC, which is translation, and we know its direction. Let's say it's a magnitude AC with multiplied by I, where I is a unit vector going to the right. As this is rotating, this is going to go to the right. It's going to be equal to, AC is equal to AB plus the relative velocity of C as seen by B, which is two components. The first one is alpha of this length BC, not that alpha, this BC length, cross product of R C relative to B, right? So this vector from B to C, minus omega square of this BC, which we don't know yet, multiplied by R C relative to B. So not to forget. Now since we know this magnitude, or we know this B value, and we know the direction, so this equation has alpha as an unknown, has omega as an unknown, and also has an AC as an unknown. So there's one equation with three unknowns. However, that equation is a vector. It's going to provide you two equations, sub-equation, because you have to separate I and J, and be able to solve two unknowns. But there's another unknown, which is the omega. So to find the omega, you have to use the relative motion analysis of the velocity to help you with omega, or you can use the IC, instantaneous center of zero velocity, to calculate omega, as we discussed in the previous. So that can be found by drawing a normal or constructing normal lines orthogonal to the path or the velocity, and then will be somewhere here, and then we use the geometry and then calculate the omega, knowing that the velocity of the point B can be found from this link. All right, so that in a nutshell is the process applied to that example. So the procedures for analysis is just to summarize what I have said. You draw the kinematic, you indicate label all the parameters that concerns for each link, and then apply the relative acceleration equation. Let's take this example. We have a rod AB. The two ends of this rod is rolling against a wall with deterministic direction. Point A is sliding downward. Therefore, point B is moving to the right. The acceleration and the absolute acceleration and the absolute velocity of point A are known. They are given. We want to find the angular acceleration of the rod, alpha, this rod, and also, let's say omega, we need it. If even not asked, but we need that. And also find the acceleration of point B. So the method to solve follows the relative motion analysis, velocity and acceleration. Since the relative velocity or relative analysis acceleration does have an omega, or the angular acceleration velocity of that rod, therefore we need to calculate its angular velocity. And to calculate the angular velocity of this rod, because it appears in that relative velocity, relative acceleration equation, we can use the instantaneous center of velocity, which is a graphical method, knowing this path of A is downward and this is to the right. We construct two orthogonal lines. One is orthogonal to VA, so this is the first line, and one is orthogonal to VB, which is this line, right? VB is to the right, the orthogonal. So that's the intersection. Now the distance from here to here, so this is 4, 5, this is 3, and since this is known, so velocity of VA, right, can be measured using the IC. So therefore, VA is equal to omega AB cross product of RA relative to IC. So RA relative to IC is this distance, right? And it's pointing from here to there, so it is, let's say, negative 3I. Since this problem is very simple, we don't need vector. We can just intuitively can know that as this is moving down, this will rotate counterclockwise, right? Meaning this will rotate counterclockwise, the entire AB. So therefore, dA, which is equal to 6, equal to 3 distance multiplied by omega. So omega equal to 6 over 3 radian per second. Again, omega is for the AB because it appears in the acceleration analysis, as we'll see here. But anyway, now, so that step has to be done. Now the question asks us how much is the alpha, or the angular acceleration, and also AB. So the first step is we have calculated omega. We put here the known A, VA, the unknown AB. AB is a vector, alpha is a vector. AB is, as a vector, is equal to the magnitude AB multiplied by I. So if I assume that J positive is upward and I positive to the right, or y x positive to the right, so this AB is equal to magnitude of AB multiplied by I, a vector, right? Now, can I calculate the velocity of AB using a relative motion analysis expression? Yes, AB is equal, as an absolute, equal to AA plus the relative velocity or relative acceleration of AB to A. Now that one, it does have two components, which is the normal and tangential. So the tangential is going to be equal to the first part alpha cross R B relative to A. So this is the vector minus omega squared multiplied by RB relative to A. Now we need to know what is alpha. Now we can assume alpha to be, since an assumption of counterclockwise is a positive, so we can say alpha is accelerating, and it's a counterclockwise, meaning it's accelerating in that direction. And if the number that shows from calculations is tend to be negative, then it means that our assumption is the opposite. So for now, we're going to say alpha is equal to a magnitude alpha. Now, since this is alpha is in 2D, so it's equal a magnitude of alpha multiplied by k, assuming this is counterclockwise, right? So alpha k, alpha. So this is bold, is the vector alpha k cross. Now, RB relative to A is a position vector from A to B, so the head is on the B. So that is simply, has two components, is the 3I minus 4J, right? 3I minus 4J. So think of it this way. Okay. So this has two components, as we know. This is the first one and the second one. So this is where we got the position. So it's a 3I positive minus 4J. Cross product minus that omega, which we found from the relative motion analysis velocity to, okay. Now, AA, we already know it is negative 5J, according to the Cartesian coordinate system we selected. AB, we don't know the value or the magnitude, we know its direction. So AB as a vector is equal a magnitude that is unknown to us, AB, but we know it's always in contact to the wall and it has a known direction, ABI, right? So we'll label that as ABI. So I'm gonna here insert the vector components and then conduct a cross product. So the cross product, you can use the cross product of a circle, unit circle. Now there's a different unit circle, sometimes arranged as I, J, and K, others define I, K, and J. As long as you memorize a method, a trick method that helps you memorize that will be okay. So for example, following this graph, K cross I is going to give you a J. So when you distribute, make sure that you follow the cross product of a method that you are familiar with. So distributing that, you're going to end up with a vector equation, which after simplifying it and collecting the i's and j in units, so you're going to end up with ABI equal to that unit, and then you have another unit or coefficient of j is that. So since the right hand side has to match the left hand side, so therefore AB has to match the coefficient of I has to match the coefficient of I in both sides. So AB equal for alpha negative 12. From that we can have one equation, and the other equation is that 0, the component of j in the left side is 0 equal to the component of the j in the right hand side, which is 3 alpha plus 11. And that's going to give you the magnitude of alpha. So upon analysis, you will find that alpha, which is the angular acceleration which we want to find, is equal to, it can be obtained from that equation. So it's going to be negative 3, so means it's our assumption, which was counterclockwise is wrong, should be therefore opposite side. So it's a 3.67 clockwise, and then substitute that into that equation. You're going to get AB. So AB is equal to 26.7 meter per second, and it's a negative, mean its direction is to the left, so it's a decelerating. So this way we finished the first part of the section. I'm going to move to the body in contact in the next section.